So this was a weekly pop quiz, structure pop quiz, the second pop quiz of the week. Any doubt in question one, part A? Any doubt? Question page number 2, part B. Any doubt? B1. Okay. The electrons in an atom up to Kr 36 are distributed in s, p, and d orbitals. State the number of occupied orbitals in an isolated atom of Kr. When we say the like isolated atom is there, you have to write the configuration for 36. So we know like 1s, then 2s, 2p, then 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, then 6s, 6p, and then 7s. So first electron 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then so on. So when we write the configuration for 36 electrons, so we have 1s2, 2s2, 2p6, 3s2, after 3s2 it will go to 3p6, then from 3p6 it will go to 4s2. So how many we have arranged? We have arranged total 20 are arranged. Then it will go to 3D. From 3D, it will go to 3D10 will be there. So means we have arranged 30 electrons. And from 3D10, it will go to 4P. So from 3D10, it will go to 4P and 4P, 6. Remember, P is a subshell. Okay. So how many how many occupied orbital? So how many s orbitals are occupied according to this? So we have 1, 2, 3, and 4. So there are 4 s orbitals which are occupied. What about p? P is a subshell. Each p subshell contains 3 orbitals, like px, py, and pz. So this is having 3 orbitals. This is having 3 orbitals. This is also having 3 orbitals. So how many orbitals are occupied? P orbitals are occupied. So total 9 p orbitals are occupied. And how many d orbitals are occupied? Because d subshell contain 5 orbitals and d10 means all of them are filled. So how many are filled? So 5 of them are filled. Is it clear? How we identify the number of orbitals? So first we write the configuration. Then according to the number of, as the orbitals, if the p orbital is complete, it means that 3 orbitals. If the p subshell is complete, it means 3 orbitals are occupied. If d subshell is complete, it means 5 orbitals are occupied. B2. Then complete the diagram to show the number and the relative energies. For silicon, so it is, because silicon is 14. When you write the configuration, 1s2, 2s2, 2p6, 3s2, 3p2, because we need 14. So 1s will have 2 electron, 2s will have 2 electron, 2p will have 6, so 1, 2, 3, 4, 5, 6. 3s will have 2, so 1, 2. 3p will have 2, so they will occupy single first. If 3p3 was there, again single. If 3p4 is there, then they will pair up. Any doubt on page 3? Page number 3, any doubts? In B2, 1B2, can't we do it No, you cannot do a hybrid state until unless it mention. Until unless they mention it is hybridized. Otherwise, you cannot. In part 4, the first ionization of energies of element in the row of a D block for scandium till copper are very similar. For all these elements, it is 4s electron that is lost first. Suggests why the first ionization energies of these elements are very similar. Look, what the ionization energy depends on? The ionization energy depends on the nuclear charge. The ionization energy, what it depends on? It depends on the nuclear charge, and it also depends on the shielding effect. So when we move across the period, the nuclear charge is increasing. Because when you move from scandium till copper, they're in the same period, same row, first row. So when they're in the same row, means they will have the same number of the shells. So when they have the same number of the shells, they will have the same shielding effect. But when we move, the proton number is increasing. So as the proton number is increasing, the nuclear charge will increase. So how you will mention or write the answer? When you write the configuration, like usually when we move across the period, the ionization energy increases. So when you write the configuration, like example, you write the configuration for scandium, which is 21. You will write 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and then 3d, because we want to make 21, so it is 10 here, 18, so 3. But in terms of energy, what will be the configuration? It will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. When you write the configuration for another element like element with 22, yeah, 3d1, sorry, not 3, 3d1. 21 I want to make. I was thinking of 23. If I have 22, so it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. But when we write in terms of energy, 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, and 4s2. So what is actually happening in the transition element? In terms of the inner shell electrons, the inner shell electrons are increasing. Like first it was 3d1, then it is 3d2, then it will be 3d3, 3d4. So as a result, when the inner shell electron increase for these elements, the shielding effect will also increase. So the nuclear charge increase. As the nuclear charge increase, what should happen? The ionization energy should increase. Should increase. And because there are more inner shell electrons, so the shielding effect increase. As the shielding effect increase, what should happen to the ionization energy or the first ionization energy? The first ionization energy should decrease. So the nuclear charge is increasing and so as a result of a nuclear charge is increasing, ionization energy increases. But the shielding effect is increasing, so ionization energy is decreasing. So as a result, both of them cancel out the effect of each other. That's why the first ionization energy of the transition element from scandium till copper, they have the same ionization energies or similar ionization energy. Is it clear? When you write the configuration, you always write the electron in the 4s first and then 3d. But when you write the configuration, you write in terms of order, the lower energy level first and the higher energy level afterwards. How did it cancel out the effect of each other? Yeah, I will look. Scandium is having 21 protons. The other element is having like 22 protons. Okay. So according to this, the ionization energy should increase. Okay. But what happened? The shielding effect means the element with the 22 should have a higher ionization. But what happened? The shielding effect, it has more electrons. How many inner shell electrons are there? 2, 4, 10, 12, 16, and 20. So 20 inner shell electrons. How many inner shell electrons for this one? So 2, 4, 6, 10, 16, and 2, 4, 6, 10, and then it is 19 inner shell electrons. So it means this element will have a greater shielding effect. So greater shielding effect, as a result, the ionization energy should decrease. So because of the proton, it should increase. Because of the shielding effect, it should decrease. So overall, what happened? It cancel out the effect of each other. Is it clear? That's why they have the similar ionization energies. Question 2. Explain why phosphorus 4 oxide has a low melting point compared to magnesium oxide. You have to compare the phosphorus 4 oxide. It's a simple covalent compound. So weak intermolecular force. Magnesium oxide is an ionic compound. So it's strong electrostatic force. You have to compare these points. One is the simple molecular structure. So weak intermolecular force. So small amount of energy can separate the molecules. Wherein magnesium oxide, it will be a giant ionic lattice. So strong electrostatic attraction, need a large amount of force to separate the ions from each other. So comparison is there, the simple covalent and the giant structure. Question 3 and 4, any doubt? Any doubt from question 3, 4? Question 3, describe the lattice structure of silicon 4 oxide. So silicon 4 oxide is a giant structure in which each silicon have a covalent 4 oxygen are bonded covalently. So it's a giant covalent structure, and there's a covalent bond between the silicon and oxygen, and the geometry, the structure, because 4 bond pairs and no lone pair, so it will be a bond angle of 109.5 or a tetrahedral structure. So mentioning the point, giant covalent structure, and because each silicon forming 4 covalent bond with oxygen, as a result, it will be a tetrahedral. In question 4, NCl decomposes according to the equation. A sealed container of volume 250 contain unreactive gas at a pressure of 1 exponent 5, 0.241 grams of NCl was injected in the sealed container. The sealed container was heated to make NCl decompose and then cool to 20. Calculate the final total pressure inside the sealed container at 25 after the NCl is fully decomposed. So first, we should know the moles of NCl3, because when it will decompose, it will give nitrogen. And initially, unreactive gas was there at the pressure of 1 exponent 5. So in a container, already there is a gas present, which was causing a pressure of 1 exponent 5 Pascal. So what we will do, we'll find the pressure, the new pressure, because of new, like this NCl3 will decompose and it give nitrogen and chlorine. So there will be a pressure due to the nitrogen and chlorine, and we work out the total pressure of these two gases by using the general gas equation. PV is equals to nRT. So first we work out the moles. So how we work out the moles? Moles equal mass in gram over molar mass. So 0.241 divided by molar mass of NCl3. Nitrogen is 14 plus chlorine is 35.5 multiplied by 3. How many moles we get for this NCl3? When you divide, what is the value for the moles? 2 exponent minus 3. Okay. So 2 exponent minus 3 moles are there for this NCl3. Now we'll use a mole ratio. So what will be the mole ratio? Like first, the mole ratio between nitrogen and NCl3. The mole ratio is 2:1. So if it is 2 into 10 to the power minus 3, so this will be x. When we cross multiply, we got 1 into 10 to the power minus 3. That is the moles of nitrogen. How many moles of chlorine will be there? The ratio is 2:3. The ratio is 2:3, so you can work out the moles of the chlorine. That is one way of doing. You can also use. So what is the value for x? If the ratio between the NCl3 and the chlorine is 2:3, so if we have 2 into 10 to the power minus 3, how many moles will be there? X cross multiply. So you got 3 into 10 to the power minus 3 moles of chlorine. So what are the total moles of the gas we get? Why aren't we? Because what we are finding, we have already a gas is there inside which was exerting a pressure of 1 exponent 5 Pascal. But when NCl3 decomposes, it produces nitrogen and chlorine. Then the nitrogen and the chlorine will also exert a pressure. No, we can, because NCl3 is a liquid. The liquid does not apply this pressure. When it decomposes, it produces nitrogen and chlorine. That is the one which applied the pressure. So what is the total moles of the gas? So what is the total moles of the gas? 3 exponent minus 3 moles of chlorine and 1 exponent minus 3 moles of nitrogen. So the total moles of the gas will be 4 into 10 to the power minus 3. The total, the sum. Is it clear? Then we work out the pressure exerted by these two gases, like using a formula PV is equals to nRT. Or you can also do, like first you find the pressure exerted by nitrogen. You will take the moles of nitrogen, then find the pressure exerted by the chlorine by using the moles of the chlorine. And then the total pressure will be the sum of the pressure of nitrogen plus chlorine plus the original pressure, which was 1 exponent 5. Or you can directly take the moles by using a formula PV is equals to nRT. So P is the pressure, V is the volume of the container, which is 250 cm cube. We have to convert into meter cube. So it should be divided by 1 million, like it will be 215 to 10 to the power minus 6. N is the number of the moles, which is 0.4 exponent minus 3 if I'm taking the combined. R is the general gas constant, 8.21 or 8.31, not 21, 8.31. And T is the temperature, that should be in Kelvin. So 20 plus 273, so it will be 393. So this P is the combined pressure of the nitrogen and the chlorine. And then the total pressure will be the pressure of the nitrogen chlorine plus the original pressure. We'll get the combined pressure which is experienced by this container. Is it clear, this question? Any doubt in this? Question 5, 6. Any doubt?